Hi everyone, my name is Sandesh and I am your peer tutor this semester. Today I will be going over homework 3, question number 5, and I will try to cover some of the misconceptions that we've been seeing on the homework or covering the parts that may seem more difficult than normal. So to begin with problem 5, we have the problem statement that we are drawing 7 cards from a 52 card deck. And for part A, we are looking for the probability that out of 7 cards, exactly 3 are aces. So let's define that event first. I will use the letter A to designate the event that 3 aces are pulled. Okay. Now, to find the probability of A, we want to find the number of elements in event A out of the total number of elements possible. Okay. And the motivation behind this is that our sample space is finite, meaning that all values in the sample space are finite. Now, what does that mean in the context of this problem? Well, in our problem, our sample space is a 52 card deck. And out of these 52 cards, we have aces, we have ones, we have twos, and we have jack, queen, and king. So clearly, the sample space is finite. It doesn't go on to infinity. Our next assumption we make here is that each outcome is equally likely. And this makes sense because if we have a 52 card deck and we randomly pick one card, the probability that it's an ace, 1, 2, 3 is all equally likely if it's a well-shuffled deck. Next, we want to kind of define what type of problem this is. So in problem A, we're pulling 3 aces from a 52 card deck, okay, out of a sample of 7. So actually, let me try to visualize this, okay? So we have a 52 card deck here. We're pulling a sample of 7, and out of those 7, we want 3 aces, okay? So this sounds like either a permutation or combination question. And if you recall, permutation and combinations involve selecting k objects out of n total objects without replacement. So in problem A, we are selecting 3 aces out of all possible aces in the 52 card deck. So in a 52 card deck, we have a total of 4 aces. Okay, so our pool of 3 aces is coming from these 4 aces. Well, if our sample size is 7 and we pull 3 aces, the other 4 cards have to be non-aces, meaning they can be any other card that's not an ace. And this is equally as important because knowing that you have one thing necessarily means that you have to have everything else in the sample. So out of our 52 card deck, if 4 of them are aces, the other 48 must be non-aces. So our 4 non-aces are coming from this subset of non-aces from the total deck. Okay. So I think we have a very clear idea of what we're looking for and where those cards are coming from. So let's tackle this probability. So first, we need to consider whether it is a permutation or a combination. Recall that permutation is when the order does matter. So, for example, if this question said, what's the probability that you get one ace on the first draw and then another ace on the third draw, or the third ace on the fifth draw, right? That's when the order would matter. However, in this question, the order does not matter because it says out of these 7 cards, include exactly 3 aces. That could mean the aces are the first 3. It could mean that the aces are the last 3 or in the middle. It doesn't matter. So the order does not matter. Therefore, it is a combination question. Okay. So the probability that we get 3 aces out of our 7 is the combination of getting 3 aces out of our 4 aces times the probability or the combinations of getting 4 non-aces out of 48 aces divided by the total number of possibilities, which is how many different ways can we pull 7 cards from the 52 card deck? So this is how many different ways can we pull 7 cards from a 52 card deck? Sorry. All right. So now we just have to figure out what N and K are for each case. And the reason I multiplied these 2 combinations in the numerator here is because both of these events have to occur simultaneously for this condition to be true. Meaning that if we get 3 aces from our 7 card sample, we must have 4 non-aces. And therefore, if it's a must, it is an and condition. So consider that as an intersection, okay? And we can multiply them without having to subtract their union because these are mutually exclusive events and you can't have 2 cards happen at the same time. You can't have 2 different cards occur in one draw, if that makes sense. So recall that N is the number of distinct objects but K is the how many objects we're picking up. So objects picked up. Okay. So in our first case in our numerator, our N will be 4 and our K will be 3. And this is because we're picking 3 aces out of 4 distinct aces from the deck, okay? And we're multiplying this by 48 choose 4. Again, this means we're picking 4 non-aces out of 48 distinct non-aces. And this is divided by 52 choose 7. Once again, this means we're picking 7 cards out of a total of distinct 52 cards. Okay. Now, this is sufficient as an answer. It shows understanding, but you can also calculate the probability mathematically. If you recall, for combinations, the formula n choose k equals n factorial divided by k factorial n minus k factorial. So for each of these events, you can calculate the numerical value. For example, for this top one here, you would do 4 factorial divided by 3 factorial, n minus 3, 4 minus 3 factorial, and you would get a numerical value there. All right. Let's move on to question part B. So for part B, it asks us to get exactly 2 kings from a sample of 7. Now, this is a very similar format to the first question, except our target is different. So we still have a 52 card deck. We still are drawing 7 cards. However, we're looking for 2 kings. So therefore, the other 5 cards must be non-kings. Okay, well, where are the kings coming from? Well, the kings are coming from the 4 kings in the 52 card deck. And the non-kings are coming from the remaining 48 non-kings in the deck. So now we know where each of the cards are coming from. Let's rewrite the probability, but this time I will define A as obtaining 2 kings from the sample of 7. So this time, let's consider for the first combination, we want 2 kings from 4 distinct kings. So we can write this as 4 choose 2. Remember, we're picking 2 out of 4 distinct kings. Next, we want 5 non-kings out of the remaining 48. And the total number of combinations is still 52 choose 7. So the total number of combinations, the 52 choose 7 tells us how many different ways can we pull 7 cards from 52 if order doesn't matter. Okay, and this is it. This is the probability of getting exactly 2 kings. Of course, you can calculate the numerical value, but this is sufficient for understanding. Now, finally, let's move on to question 3, or C. So in this one, our probability is, we're looking for the probability of getting exactly 3 aces or exactly 2 kings. Or both. Well, what does that mean? Well, if we draw our space here and have our Venn diagrams, let's let one event be getting 3 aces, the other event getting 2 kings. Well, the probability of getting 3 aces is the left circle. Probability of getting 2 kings is the right circle. And the probability of getting both is the intersection, right? So really what this is saying is we get either 3 aces or 2 kings. It is the union of both events. Okay. So for the union, recall the formula that A union B equals the probability of A plus the probability of B minus the probability of A intersection B. Now, the probability of A corresponds to the probability of getting exactly 3 aces. The probability of B is the probability of getting exactly 2 kings. Thankfully, we solved for those in part A and part B, but it is the similar method, if you think about it. The probability of A, we said, for getting 3 aces was 4 choose 3, 48 choose 4, over 52 choose 7. The probability of B getting exactly 2 kings is 4 choose 2, 48 choose 5, over 52 choose 7. Now we just need to figure out this last probability. The probability of getting A and B. Well, let's consider our diagram once again. So we're getting 7 cards from a 52 card deck. Now, and A and B occurring means we get 3 aces and 2 kings from our 7 card sample. So if we draw this out, we're getting 3 aces, 2 kings. And remember, it's equally as important to know that the remaining cards must be non-aces and non-kings. So out of our 7, if 3 are aces, 2 are kings, we have 2 cards left. So these are 2 non-aces, non-kings. So where are these cards coming from? Well, once again, our 3 aces are coming from, sorry, give me a second. Our 3 aces are coming from 4 aces in the deck. Our 2 kings are coming from the 4 kings in the deck. Sorry if this diagram is a little bit confusing. And if 4 kings are aces and if 4 cards are kings and 4 cards are aces, the remaining 44 cards are non-aces and non-kings. So now we have a clear idea of where our cards are coming from. We can write this probability out. So remember, we need 3 aces, we need 2 kings, and we need 2 non-aces, non-kings. If all of these occurrences have to occur at the same time, we have to multiply their combinations together. So for aces, we are picking 3 aces from 4 aces in the deck. We are picking 2 kings from the 4 kings in the deck, and we are picking 2 non-aces, non-kings from the 44 cards remaining. And the total number of events is still 52 choose 7. Okay, remember, the numerator, we're multiplying all of these together because all these events have to occur. And since we can't pull 2 different cards in one draw, since they're independent of each other, we're allowed to multiply their combinations. Okay. And that is your final answer. Once again, you can calculate the numerical value if you would like, or if you have a powerful enough calculator. But I hope this clears up some of the confusion for question number 5 on homework 3. And if you have any questions, feel free to email me. Thank you.